How did life begin? It's one of the most profound questions humanity has ever asked, and yet, despite centuries of searching, the answer remains just out of reach. But what if we told you the secret might be written in the stars? Imagine this: billions of years ago, long before Earth even existed, the building blocks of life were already forming in the cold, vast emptiness of space. Organic molecules, the very ingredients that make up everything from the cells in your body to the trees outside your window, might have been born among the swirling dust and gas of cosmic nurseries. And today, scientists are piecing together an extraordinary puzzle. How did these molecules come to be, and what role did they play in seeding life across the universe? This isn't just a story about chemistry or distant galaxies, it's a saga about us. Every atom in your body was forged in the heart of a dying star, and the molecules that make life possible might have traveled across the cosmos before finding their way here. But how? That's where things get truly fascinating. Over the years, researchers have proposed dozens of mind-bending theories. Some sound like science fiction, others are backed by cutting-edge experiments, but all of them point to one incredible truth: the universe might be hardwired to create life. From lightning strikes on a primordial Earth to icy comets delivering life's blueprints from deep space, the possibilities are as thrilling as they are mysterious. So buckle up, because we're about to dive into 30 of the most groundbreaking ideas scientists have come up with to explain the origins of organic molecules in the universe. Some will challenge what you thought you knew about life's beginnings. Others might leave you staring at the night sky with a whole new sense of wonder. Whether it's the hidden chemistry of distant nebulae or the tiny, resilient molecules hitching rides on asteroids, each theory is a piece of a puzzle that could rewrite our understanding of existence itself. And by the end of this journey, you'll see the cosmos, and maybe even yourself, in a way you never expected. The story of life's origins is being written right now, and you're about to get a front row seat. One of the most enduring theories about life's origins starts right here on Earth, in what scientists call the primordial soup. Picture our planet over 4 billion years ago, a roiling, chaotic place with erupting volcanoes, crashing thunderstorms, and vast oceans simmering under a young, fierce sun. In this turbulent environment, the building blocks of life may have been cooking up in Earth's ancient waters, a thick broth of simple molecules stewing together until something extraordinary emerged. The idea, known as the Primordial Soup Hypothesis, suggests that organic molecules like amino acids, the very foundation of proteins, were forged through chemical reactions powered by natural energy sources. Lightning strikes, volcanic heat, and even ultraviolet radiation from the sun could have acted like a cosmic mixer, stirring simple compounds like water, methane, and ammonia into more complex structures. It's almost like nature's own chemistry lab, where random chance and raw energy conspired to create the ingredients for life. This theory gained legendary status in the 1950s, thanks to a groundbreaking experiment by Stanley Miller and Urey. They recreated Earth's early conditions in a lab, sealing water, methane, ammonia, and hydrogen in glass flasks, then zapping the mixture with electrical sparks to simulate lightning. Within days, the experiment produced something astonishing. Amino acids, the fundamental components of proteins, had formed spontaneously. It was the first real proof that life's raw materials could arise from simple chemistry. But like any great scientific idea, the primordial soup hypothesis has faced its share of challenges. Some researchers argue that Earth's early atmosphere might not have been as rich in methane and ammonia as Miller and Urey assumed. Others point out that while amino acids are essential, they're just one piece of a much larger puzzle. How did these molecules assemble into something as complex as a living cell? And yet, despite these questions, the experiment's legacy endures. It proved that under the right conditions, the universe has a knack for creating the ingredients of life. What makes this theory so compelling is its simplicity. No need for interstellar comets or cosmic accidents, just Earth's own volatile youth, turning simple elements into life's first sparks. Maybe it didn't happen exactly as Miller and Urey imagined, but their work opened the door to a stunning realization. The universe might be hardwired to build the blocks of life given the right time and place. Now let's plunge into the ocean's crushing depths where scalding water, toxic chemicals, and crushing pressure might have sparked life's first molecules. Far from sunlight and storms, hydrothermal vents on the seafloor create a surreal landscape of towering chimneys spewing superheated, mineral-rich fluids. These alien environments, once thought inhospitable to life, are now leading suspects in the mystery of organic molecule formation. The vents work like natural chemistry factories. As seawater seeps into Earth's crust, it heats to extreme temperatures, dissolving metals and minerals before erupting back into the icy ocean. This collision of scalding and freezing water creates thermal gradients, nature's version of a battery, providing energy to drive chemical reactions. But the real magic happens when these mineral-rich fluids meet the vent's porous rock structures. Metals like iron and nickel act as catalysts, helping simple molecules like carbon dioxide and hydrogen bond into more complex organic compounds. What's astonishing is how perfectly these conditions mirror life's basic requirements. The vents offer shelter from Earth's violent early surface, steady energy sources, and mineral surfaces where molecules could cling and interact. Some experiments even show that vent chemistry can produce amino acids and lipids, key ingredients for cells. And here's the kicker. The vent's microscopic pores resemble cell membranes, creating natural compartments where molecules could concentrate and react. It's as if the Earth itself was sculpting the precursors of life in these underwater laboratories. This theory gained traction when scientists discovered entire ecosystems thriving around modern vents, powered not by sunlight but by chemosynthesis bacteria converting vent chemicals into energy. If life can flourish here today, why not 4 billion years ago? The vent's stability and longevity make them ideal incubators, allowing slow, incremental chemistry to build complexity over millennia. Yet mysteries remain. While vents excel at creating simple organics, bridging the gap to full-fledged life is still a puzzle. Could random chemistry in a vent's pores really lead to self-replicating molecules? Some researchers argue vents are just one piece of the story, while others see them as life's most promising cradle. Either way, these deep-sea crucibles remind us that life might not need a gentle beginning. It could have emerged in the most extreme places imaginable. What if Earth didn't cook up life's ingredients at all? What if they were delivered from the stars? Enter Panspermia, the provocative theory that organic molecules hitched rides on comets and meteorites, raining down on our planet like cosmic grocery bags. This idea turns the search for life's origins inside out. Instead of starting here, the story might begin in the freezing depths of interstellar space, where complex molecules could have formed long before our solar system even existed. Take the Murchison meteorite, a space rock that crashed into Australia in 1969. When scientists cracked it open, they found a treasure trove, over 90 different amino acids, some never seen on Earth. Even more astonishing, these molecules showed a slight preference for left-handedness, a mirror image to the right-handed ones common in nature. That's a big deal because life as we know it relies exclusively on left-handed amino acids. Could this mean the building blocks of life weren't just floating around in space but were already pre-selected for biology? The plot thickens when you consider where these molecules might have come from. Far beyond our solar system, in the icy clouds between stars, telescopes have detected complex organics like formaldehyde and even sugar molecules. These cosmic chemistry labs, bombarded by radiation and chilled to near absolute zero, might be ideal factories for forging life's ingredients. And when comets form from these clouds, they could lock these molecules inside like cosmic time capsules, preserving them for billions of years until they collide with planets like Earth. Recent exoplanet discoveries add fuel to the fire. We've found worlds orbiting other stars with water, carbon, and even potential organic molecules in their atmospheres. If life's ingredients are common across the galaxy, Panspermia becomes less of a fringe idea and more of a cosmic inevitability. Imagine, a single microbe-rich comet could theoretically seed life across multiple star systems, turning the universe into a vast interconnected web of shared biology. But Panspermia isn't without its critics. The journey through space is brutal, intense radiation, temperature extremes, and the fiery plunge through a planet's atmosphere would seem to destroy any delicate organic cargo. Yet experiments show some tough molecules, even microbes, can survive these conditions. Tardigrades, those nearly indestructible water bears, have endured the vacuum of space in tests. If they can do it, why not simpler, hardier molecules? The real game changer would be finding definitive proof, like discovering a microbe on Mars with DNA eerily similar to Earth. Until then, Panspermia remains a tantalizing what if. But whether you buy into it or not, this theory forces us to think bigger. Life on Earth might not be an isolated accident but part of a grand interstellar cycle where comets are the couriers and the universe itself is the cradle. Deep in the cold, dark stretches between stars, where temperatures hover just a few degrees above absolute zero, something extraordinary happens. Chemistry doesn't stop. It thrives. These interstellar molecular clouds, vast regions of gas and dust spanning light years, might seem like frozen wastelands, but hidden within their icy grains lies a secret, their cosmic kitchens, quietly assembling the very molecules that could become the foundation of life. Take formaldehyde and hydrogen cyanide, two seemingly toxic compounds you'd never associate with biology. Yet in the vacuum of space, these molecules behave differently. Floating among the dust grains, they stick to icy surfaces like microscopic scaffolding. Then, bathed in faint starlight or zapped by cosmic rays, they start reacting. Slowly, over millions of years, simple atoms rearrange into more complex structures like sugars and even amino acids. It's a paradox. The harshness of space becomes the perfect lab for organic chemistry. Radio telescopes have caught glimpses of this process in action. In the Orion Nebula, scientists detected glycolaldehyde, a simple sugar floating freely in one of these clouds. Elsewhere, they've found ethanol, the same alcohol in your drink, drifting between the stars. These discoveries hint at something profound. The universe might have been prepping life's ingredients long before planets like Earth were even born. What makes these clouds such efficient factories? Three things: time, surface area, and cold. Unlike Earth's chaotic early environment, molecular clouds offer stability. Reactions unfold at a glacial pace, but with trillions of dust grains acting as tiny reaction chambers, complexity builds. And the extreme cold is actually an asset. It keeps fragile molecules from breaking apart, allowing them to grow step by step. Some experiments even show that under space-like conditions, these ices can form nucleobases, the very letters of DNA's genetic code. But how do these molecules end up on planets? When a cloud collapses to form a new star system, much of that organic, rich ice gets baked into comets and asteroids. Later, during the solar system's chaotic youth, these celestial bodies bombard young worlds, delivering their precious cargo. It's like the universe has a built-in delivery system for life's starter kit. This theory reshapes how we see our place in the cosmos. If molecular clouds are universal assembly lines, then the ingredients for life might be scattered everywhere, waiting for the right planet to give them a home. Suddenly, the search for life beyond Earth isn't just about finding water or the right temperature. It's about tracing the cosmic supply chain that might have stocked the entire galaxy with life's raw materials. Imagine standing on a beach 4 billion years ago, but this shoreline doesn't look anything like the ones we know today. Instead of golden sand, the ground shimmers with strange radioactive minerals pulsing with energy as waves crash against them. This surreal setting might hold the key to one of the most unexpected theories about life's origins, the radioactive beach hypothesis. Here's the idea. Early Earth shorelines could have been littered with minerals like uranium and thorium, remnants of ancient rock formations, or even meteoric debris. These elements naturally emit radiation, not just the dangerous kind we associate with nuclear disasters, but at lower levels a steady trickle of energy. And that energy might have been exactly what simple molecules needed to jumpstart the chemical reactions leading to life. Think of it like a slow cooker for organic chemistry. While lightning and hydrothermal vents offer bursts of intense energy, radioactive minerals provide something different, a constant, low-level hum. This steadiness could have allowed delicate molecular structures to assemble gradually without being ripped apart by sudden jolts. Picture amino acids forming in tidal pools, their bonds strengthened by gentle radiation over countless tides. Scientists have tested this in labs by exposing simple chemical soups to controlled radiation. The results, amino acids and even more complex molecules, can indeed form under these conditions. One experiment used uranium salts in water, mimicking those primordial beaches, and found that radiation helped link simple carbon compounds into longer chains, a crucial step toward life's complexity. But what makes radioactive beaches stand out from other theories? Two things. First, the tidal zone offers a perfect Goldilocks environment, not too wet, not too dry. Molecules could concentrate in shallow pools as water evaporated, then get reshuffled by waves over and over. Second, radiation doesn't just supply energy, it can also act as a selective force. Some molecules handle radiation better than others, meaning nature might have been subtly favoring the most resilient structures, paving the way for hardy early life. Of course, there are skeptics. Too much radiation can destroy organic molecules just as easily as it creates them, and we don't know exactly how common these radioactive beaches were. But the theory gains traction when you look at extremophiles, modern microbes thriving in nuclear waste or deep underground in radioactive rock. If life can endure those conditions today, why couldn't it have begun there? The bigger picture here is tantalizing. If radioactive beaches played a role, it suggests life might emerge in places we'd never expect, not just warm tidal pools or volcanic vents, but anywhere with the right mix of energy and patience. That expands the possibilities for where we should search, both on Earth and beyond. Imagine distant exoplanets with shores glowing faintly from radioactive sands, quietly cooking up their own versions of life's first molecules. The universe, it seems, has more than one recipe for sparking chemistry into biology. Picture a prehistoric Earth, its skies fractured by constant electrical storms. Not just the occasional lightning bolt we see today, but relentless planet-wide discharges crackling through thick, swirling clouds. This wasn't just a dramatic light show. It could have been the universe's way of jump-starting life's chemistry through a process called electric spark synthesis. The idea goes beyond Miller and Urey's classic lightning experiments. While their work proved that sparks could create amino acids, newer research suggests atmospheric electricity might have done far more. Take sprites, for example, those mysterious red flashes that dance above thunderstorms. These colossal electrical discharges, stretching 50 miles into space, carry energies dwarfing typical lightning. When scientists simulate sprite-like conditions in labs, something remarkable happens. The sparks generate not just amino acids, but also nucleobases, the very alphabet of DNA. Then there's corona discharge, a subtle cousin of lightning. Instead of a single explosive bolt, it's a continuous glow, like the eerie halo around ship masts during storms. This gentler, sustained energy might have been perfect for coaxing delicate molecules into existence without tearing them apart. Experiments show corona discharges can produce complex sugars, even under atmospheric conditions, unlike Miller and Urey's assumptions. What's truly fascinating is how these electrical phenomena could have created patterns. Lightning doesn't strike randomly, it follows atmospheric currents often recurring in the same areas. Over millennia, these hotspots might have acted like natural reaction chambers, concentrating and refining organic molecules in specific regions. Imagine shallow pools near volcanic fields, repeatedly zapped by storms, their waters enriched with each strike until they became primordial incubators. But electricity's role might extend beyond Earth. Mars, for instance, has massive dust storms that generate planet-wide static charges. If early Mars had even a thin atmosphere, these discharges could have cooked up organics long before they appeared here. Suddenly, electric spark synthesis isn't just an Earth-bound curiosity. It's a universal mechanism crackling across countless worlds. Of course, puzzles remain. How did these electrically forged molecules escape destruction from subsequent strikes? Could they really accumulate fast enough to matter? Yet when you consider how many organic molecules modern thunderstorms still produce, plus the discovery of similar compounds in Martian meteorites, it's clear the universe has a penchant for turning sparks into chemistry and chemistry into the beginnings of life. This theory electrifies the search for life's origins quite literally. It suggests that anywhere with a turbulent atmosphere and energy to spare might become a crucible for life's ingredients. Not just in the distant past, but perhaps right now on exoplanets we've yet to discover, the same celestial sparks could be weaving the same ancient magic. Stacks of wet clay might seem like an unlikely birthplace for life, but these humble minerals could have been the universe's first molecular architects. Picture Earth's ancient riverbeds and tidal flats, their surfaces coated with layered silicate clays, each microscopic sheet acting like a tiny workbench, arranging chaotic molecules into something far more organized. This isn't just dirt we're talking about, it's a natural nanotechnology lab where chemistry gets a helping hand from structure. The magic lies in clay's unique properties. Its surfaces carry subtle electrical charges, attracting and holding molecules in precise arrangements. Imagine amino acids drifting in water, bumping randomly until they stick to a clay sheet, lined up like beads on a string. Suddenly, they're close enough to react, forming chains that might eventually become proteins. Even more intriguing, some clays contain metal ions that act as catalysts, speeding up reactions that would take millennia in open water. It's as if the Earth provided its own molecular assembly line, with clay as the factory floor. One experiment brought this theory to life. Scientists mixed simple organic compounds with montmorillonite clay, a common mineral found in volcanic ash. Within days, the clay's surface had coaxed these molecules into forming RNA-like strands hundreds of units long. RNA is life's Swiss Army knife, capable of both storing genetic information and catalyzing reactions. If clays could build RNA precursors, they might have bridged the gap between chemistry and biology. But the real genius of clay catalysis goes beyond mere chemistry. These minerals self-organize into repeating layers, creating sheltered pockets where delicate molecules could accumulate without being washed away. Some clays even swell and shrink with changes in moisture, acting like a primitive pump, concentrating reactants during dry periods, then mixing them when water's returned. This cyclical process mirrors the rhythms of tidal pools or seasonal lakes, offering a natural mechanism for trial and error over geologic timescales. Critics argue that while clays excel at assembly, they might struggle with the complexity needed for true replication. Yet recent discoveries add weight to the idea. Hydrothermal vents often spew clay-rich particles, suggesting these minerals could have worked in tandem with other environments. Even meteorites contain layered silicates, hinting that clay's catalytic role might not be unique to Earth. The implications are profound. If unassuming minerals could guide life's molecules into existence, then the recipe for biology might be simpler than we thought. No need for elaborate machinery or rare conditions, just the right scaffolding, patience, and a little help from Earth's geology. Suddenly, the search for life's origins isn't just about finding the right chemicals, but the surfaces that could have given them meaning. Cosmic rays, those invisible bullets of energy hurtling through space at nearly the speed of light, might seem like agents of destruction, slamming into molecules and tearing them apart. But what if these violent particles were actually cosmic sculptors, carving the first organic building blocks of life from raw atomic debris? This counterintuitive idea, known as cosmic ray polymerization, suggests that the universe's most energetic radiation didn't just break things down, it built them up one high-energy collision at a time. Picture a young Earth, its thin atmosphere no match for the relentless barrage of protons and atomic nuclei from distant supernova. As these particles ripped through the air, they didn't just leave trails of ionized gas, they sparked cascades of secondary reactions. When a cosmic ray strikes a molecule of methane or carbon dioxide, the impact can strip away electrons, creating highly reactive fragments. Like chemical matchmakers, these charged fragments then seek out other molecules, forcing marriages between compounds that would normally ignore each other. Over millennia, this chaotic dance could have assembled carbon atoms into long chains, forming the backbone of complex organics. Lab experiments back this up. When scientists simulate cosmic rays by blasting simple gas mixtures with particle accelerators, something remarkable happens. The chaos creates order. Amino acids like glycine emerge from the wreckage, along with ring-shaped molecules similar to those in DNA. Even more compelling, these reactions work under conditions mimicking the upper atmosphere. No liquid water or special surfaces required. It's as if the universe hardwired a fail-safe mechanism. Where other energy sources fail, cosmic rays step in, knitting molecules together against all odds. The real twist: this process might explain why we find organic molecules in the most hostile places imaginable. Saturn's moon Titan, with its methane lakes and nitrogen haze, shouldn't be able to sustain complex chemistry, yet its atmosphere is laced with organic compounds. Cosmic rays could be the invisible chefs cooking up these molecules right in the frigid void. Even interstellar dust clouds bombarded by radiation for eons show traces of molecular complexity that defies conventional chemistry. But here's the fascinating paradox: while cosmic rays can create, they can also destroy. The same particles that build amino acids in one collision might obliterate them in the next. This seesaw effect suggests life's ingredients didn't form in one grand event, but through a slow, grinding cycle: creation and destruction locked in a billion-year tug of war, with complexity gradually winning out. What makes this theory so compelling is its universality. Unlike lightning or hydrothermal vents, cosmic rays permeate every corner of the galaxy, raining down on planets, moons, and even free-floating asteroids. If this mechanism works, then the raw materials for life aren't rare treasures, they're inevitable byproducts of a universe teeming with energy. Suddenly, the question isn't, could life arise elsewhere? But how could it not? Yet mysteries linger. Can random high-energy collisions really steer molecules toward biological relevance? Or is this just another piece of a much larger puzzle? Either way, cosmic ray polymerization forces us to rethink the boundaries of chemistry. Life's beginnings might not have required a sheltered pond or a deep-sea vent, just the relentless, creative violence of the cosmos itself, turning chaos into the first whispers of order. Volcanoes aren't just forces of destruction, they might have been crucibles of creation, where toxic gases collided to forge life's earliest ingredients. Forget the stereotypical lava flows for a moment. The real magic happened in the plumes of gas billowing above these fiery giants. Sulfur dioxide, carbon monoxide, and other noxious fumes we associate with deadly environments today could have been the unlikely midwives of organic chemistry billions of years ago. Picture Earth's early volcanoes, far more numerous and explosive than modern ones. Their eruptions didn't just spew rock and ash, they pumped the atmosphere full of reactive gases, creating a planetary-scale chemistry experiment. When sulfur dioxide meets carbon monoxide in the presence of ultraviolet light or heat, something extraordinary happens. The molecules rearrange, forming carbonyl sulfide. This simple compound acts like a molecular glue, helping amino acids link together into chains. It's as if volcanoes were quietly knitting the fabric of life in their smoky breath. Lab experiments reveal even wilder possibilities. Mix hydrogen sulfide, another volcanic staple, with carbon dioxide under simulated eruption conditions, and you get thioesters, energy-rich molecules that modern cells use to power their metabolism. Even formaldehyde, a key building block for sugars, forms readily in these gaseous cocktails. The implications are staggering. Instead of relying on gentle tidal pools or deep sea vents, life's first steps might have unfolded in the scalding, acidic clouds above raging volcanoes. What makes this theory so compelling is its sheer brutality. Most origin scenarios focus on sheltered environments, but volcanic chemistry thrives in chaos. The constant churn of eruptions would have created endless opportunities for trial and error, molecules forming in one plume, surviving long enough to rain down into cooler environments below. Over millennia, these cycles could have concentrated organics in volcanic lakes or nearby oceans, creating reservoirs of prebiotic material. Yet the most surprising twist comes from beyond Earth. Venus, with its runaway greenhouse effect and sulfuric acid clouds, shows traces of carbonyl sulfide in its atmosphere, a gas that on Earth is almost exclusively tied to biological activity. If volcanic reactions can produce this molecule abiotically, it forces us to rethink how we interpret potential signs of life on other worlds. Maybe what we've been calling biosignatures are just the exhaust fumes of a planet's volcanic adolescence. Critics point out the obvious hurdle. Volcanic gases are harsh, often breaking down complex molecules as quickly as they form, but nature loves balance. Just as desert cacti store water between rare rains, volcanic regions might have offered microenvironments like condensate droplets in cooler zones of plumes, where delicate molecules could accumulate between eruptions. It's a reminder that life doesn't need perfect conditions, just persistent ones. This theory doesn't just expand where we look for life's origins, it transforms how we see volcanoes themselves. No longer just destroyers, they become cosmic alchemists, turning poison into possibility. And if that's true on Earth, then active volcanic worlds like Jupiter's moon Io or distant exoplanets with supervolcanoes might be quietly cooking up their own organic experiments right now. The universe, it seems, has a flair for turning its most violent processes into creative forces. Imagine waves lapping at the rocky edges of a prehistoric shoreline, each tide carrying away salt water but leaving behind something extraordinary, tiny pools brimming with concentrated chemical potential. These tidal zones might seem like humble settings compared to volcanic fury or interstellar drama, but their quiet rhythm could have been the metronome that set life's molecular dance in motion. The tidal pool cycling theory proposes that the simple act of water evaporating and refilling over and over may have been the universe's way of distilling chaos into complexity. Here's how it works. When shallow pools evaporate under the sun, dissolved molecules don't just vanish, they crowd closer together like strangers pressed into a shrinking room. Amino acids that might have drifted harmlessly apart in open water suddenly find themselves shoulder to shoulder, primed to react. Then, when the tide rushes back in, fresh water sweeps in new ingredients, resetting the stage for another round of concentration. This cycle isn't just mixing, it's editing. Over thousands of repetitions, only the most stable molecular partnerships survive while weaker ones wash away. Lab experiments reveal the power of this process. Scientists simulating tidal cycles with simple organics watched as these molecules linked into chains 10 times longer than those formed in static solutions. Even more striking, the wet-dry cycles encouraged the emergence of proto-cell structures, bubble-like membranes that self-assembled at the water's edge, trapping molecules inside. It's as if the tides themselves were teaching chemistry how to compartmentalize, a critical step toward true cells. But the real genius of tidal cycling lies in its versatility. Unlike specialized environments like hydrothermal vents, coastlines offer endless variations: rocky outcrops with mineral catalysts, clay-rich shallows for molecular scaffolding, even volcanic beaches adding heat and reactive metals. Each pool becomes a unique experiment, testing different combinations of chemistry and energy. Some might fail, but others could stumble onto the right sequence by chance, their successes preserved in the next tide. A fascinating twist comes from meteorology. Early Earth's faster rotation meant shorter days. Tides may have cycled every 6 hours instead of 12, accelerating the molecular trial and error process. Combine that with the moon being closer, generating stronger tidal pulls, and you have a planetary-scale pump, relentlessly concentrating and refreshing primordial soups around the clock. Critics argue that tidal pools lack the energy sources of lightning or vents, but nature is resourceful. Sunlight could drive photochemical reactions during dry phases, while minerals like zinc sulfide, common in coastal rocks, might have acted as light-activated catalysts. Even wave action could provide mechanical energy, churning molecules into new configurations. The legacy of these pools might still be written in our cells. Modern organisms retain molecular machinery tuned to rhythmic changes in salinity and hydration, echoes perhaps of life's earliest dance with the tides. And if this theory holds, it suggests that any world with liquid and gravity could host similar nurseries. Picture Mars' ancient shorelines, now dry for eons, their chemistry frozen mid-cycle, or exoplanet coasts bathed in the tug of twin moons, their tides working overtime to brew life's beginnings. The universe, it seems, has a way of turning even the simplest rhythms into the foundations of complexity. Deep beneath the ocean's surface, where sunlight never reaches and pressure could crush a submarine, lies one of the most fascinating candidates for life's birthplace, not in the water itself, but in the labyrinth of mineral deposits surrounding hydrothermal vents. The iron-sulfur world hypothesis turns the spotlight onto these unassuming metallic compounds, suggesting they did more than just line the seafloor. They might have acted as nature's first batteries, powering chemical reactions that eventually gave rise to metabolism itself. At the heart of this theory are simple minerals like pyrite, better known as fool's gold. These crystalline structures, rich in iron and sulfur, have a peculiar talent. Their surfaces can shuffle electrons like a deck of cards, turning them into natural catalysts for redox reactions. That's the same basic process cells use today to generate energy, only here it wouldn't require any biology at all. Picture tiny pores in the vent's mineral walls, where hot, mineral-laden fluids meet the cold ocean water. The iron and sulfur in these minerals could have acted like microscopic power stations, driving the conversion of simple molecules like carbon dioxide and hydrogen into more complex organics. What makes this idea so compelling is how closely it mirrors modern biochemistry. Deep inside your cells right now, enzymes called iron-sulfur clusters are doing nearly the same thing, helping transfer electrons to produce energy. It's as if life didn't invent these mechanisms from scratch but borrowed them directly from the geology that surrounded it. Some scientists even describe these mineral surfaces as proto-enzymes, inorganic templates that life later refined into the sophisticated machinery we see today. Experiments back this up. When researchers simulate ancient vent conditions by mixing iron, sulfur, and simple gases, they observe something remarkable: the formation of acetate, a molecule central to metabolism. Even more striking, these reactions can string together carbon atoms into longer chains, mimicking how modern cells build fatty acids. And here's the kicker. The process generates tiny electrical currents, suggesting these minerals didn't just passively host reactions, they actively powered them, like a primordial version of the energy currency ATP that fuels all life today. But the iron-sulfur world isn't just about energy, it's also about shelter. The vent's porous mineral structures create countless microscopic chambers, each one a potential test tube for early chemistry. Molecules forming in one pore could diffuse to another, creating gradients that mimic the compartmentalization of modern cells. Some models suggest these mineral labyrinths might have even guided the assembly of RNA-like molecules, bridging the gap between chemistry and genetics. Critics raise valid questions. Could random mineral chemistry really lead to something as precise as metabolism? And if the vents were such perfect incubators, why haven't we found fossilized evidence of these prebiotic reactions? Yet the theory gains strength from its universality. Iron and sulfur are among the most abundant elements in the universe, found everywhere from meteorites to Martian soil. If they could kickstart life here, why not on other worlds with similar geology? This theory rewrites the story of life's origins from the ground up, or more accurately, from the mineral up. It suggests that before there were cells, before there was DNA, there were rocks, ordinary, unglamorous rocks, quietly conducting the universe's first experiments in energy and organization. And that changes how we look for life beyond Earth. Maybe we shouldn't just scan distant planets for water or oxygen. Maybe we should be searching for the telltale signatures of iron and sulfur, the silent architects of biology's first sparks. Out in the frozen reaches of space, where temperatures plunge hundreds of degrees below zero, an unexpected alchemy takes place, one powered not by heat or lightning, but by the soft glow of starlight. Imagine vast clouds of methane ice clinging to interstellar dust grains, their crystalline structures quietly absorbing ultraviolet radiation from nearby stars. This silent, slow-motion chemistry might hold the key to one of the universe's best-kept secrets: how simple ices transform into the complex organic molecules that seed life. Photochemical synthesis flips the script on traditional origin stories. Instead of relying on Earth's violent early conditions, this process unfolds in the serene cold of molecular clouds, where UV light acts like a cosmic sculptor. When starlight hits frozen methane, it doesn't just bounce off, it gets absorbed, transferring energy that breaks molecular bonds and creates reactive fragments. These fragments, desperate to stabilize, latch onto nearby atoms, forging new and more complex arrangements. Over millennia, this gentle but relentless process can build molecules like ethanol, formaldehyde, and even amino acids, all without liquid water or planetary surfaces. Laboratory experiments have brought this theory to life. Scientists recreate space-like conditions by freezing methane, ammonia, and water in vacuum chambers, then bombarding them with UV light. Within days, the colorless ice develops a yellowish tint, a visible sign of organic chemistry at work. Analyzing these irradiated ices reveals a stunning variety of compounds, including some found in meteorites like the Murchison specimen. One study even detected the sugar glycolaldehyde, a molecule essential for forming RNA, emerging from this simulated starlight chemistry. What makes photochemical synthesis so compelling is its universality. Unlike hydrothermal vents or tidal pools, which require specific planetary conditions, this process works anywhere there's ice and starlight, which means nearly every corner of the galaxy. Europa's icy crust, Pluto's frozen plains, or the rings of Saturn could all be hosting similar reactions right now. Even more intriguing, some of these space-borne molecules might be pre-selected for life. UV light tends to produce certain molecular shapes preferentially, mirroring the biases seen in biological systems, yet mysteries remain. While photochemistry excels at creating building blocks, can it assemble them into something resembling life's complexity? And how do these molecules survive the journey from space to planetary surfaces? Recent studies suggest cosmic ices might shield delicate organics like a time capsule, releasing them only when warmed, say, by a young planet's formation or a comet's impact. This theory stretches our imagination. Life's ingredients might not have been forged in Earth's furnaces, but in the quiet, frozen darkness between the stars, sculpted by the same light that now fills our skies. It's a reminder that the universe writes its recipes in photons and ice, and that the spark of life could be waiting, frozen in time, on countless worlds we've yet to discover. Asteroid impacts are often painted as harbingers of destruction, cataclysmic events that wiped out the dinosaurs and scarred planetary surfaces. But what if these violent collisions also played a creative role, acting as cosmic chemistry sets that forged the very molecules life needed to emerge? This is the heart of impact shock chemistry, a theory that turns our understanding of collisions upside down by revealing how chaos and creation can exist side by side in the universe's most explosive moments. Picture a massive asteroid slamming into Earth's primordial oceans. The immediate aftermath is apocalyptic searing heat, crushing pressure waves, and vaporized rock. Yet within that maelstrom, something unexpected happens. The sudden energy release doesn't just destroy, it rearranges. Simple molecules like water, carbon dioxide, and nitrogen, subjected to extreme temperatures and pressures, snap apart and recombine into more complex forms. Laboratory experiments mimicking these conditions show that impact shocks can synthesize amino acids, sugars, and even nucleobases, the raw materials of DNA, in mere seconds. It's as if the universe took a sledgehammer to basic chemistry and by sheer force hammered it into something richer. But the real surprise isn't just the molecules that form, it's where they end up. The same impact that vaporizes surface material also launches plumes of gas and dust high into the atmosphere. As these plumes cool, they condense into tiny, organic-rich particles that rain back down like a nutrient shower. Some models suggest these post-impact fertility cycles could have delivered prebiotic material across vast stretches of the planet, seeding multiple environments at once. Imagine a single asteroid strike acting as both a crucible and a distributor, scattering life's potential ingredients far and wide. The evidence isn't just theoretical. Meteorites like the one that fell near Murchison, Australia, contain not only amino acids but also complex organic compounds that seem to have formed under high-energy conditions. Even more compelling, impact craters on Earth, like the Sudbury Basin in Canada, show traces of ancient hydrothermal systems that could have nurtured post-impact chemistry for millennia. These sites become natural laboratories where destruction transitions seamlessly into construction, proving that the line between chaos and creation is thinner than we thought. Of course, skeptics raise valid questions. Could delicate organic molecules survive the initial inferno? Recent work suggests the key lies in timing. While the impact's core is hellishly hot, its shockwaves create gradient zones of varying temperature and pressure where some regions become protective pockets, shielding fledgling molecules from complete breakdown. It's a cosmic balancing act, enough energy to spark new chemistry, but not so much that everything gets annihilated. This theory reshapes how we view not just Earth's history, but the potential for life elsewhere. Mars, for instance, endured even heavier bombardment in its youth. If impacts could forge and deliver organics here, why not there? Or on icy moons like Europa, where collisions might have melted subsurface oceans, mixing space-borne organics with liquid water. Suddenly, impact shock chemistry isn't just a footnote in life's origin story, it's a universal mechanism, turning celestial violence into a creative force across the cosmos. The implications run deeper. If life's building blocks can emerge from the most violent events imaginable, then the universe might be biased toward chemistry that resets and rebuilds. Every extinction-level impact could also be a genesis in disguise, clearing the slate while simultaneously scattering the seeds for what comes next. It's a humbling reminder that creation and destruction aren't opposites, they're partners in an endless cosmic dance. Saturn's moon Titan offers a glimpse into an alien world where thick orange haze blankets the sky, a swirling organic soup that might hold clues to Earth's own chemical past. Scientists now believe similar atmospheric hazes could have shrouded our planet billions of years ago, acting as invisible factories for life's precursors. Unlike the clear blue skies we know today, early Earth's atmosphere may have resembled Titan's smoggy veil, with sunlight breaking down methane and nitrogen to form complex organic particles that rained steadily onto the surface like cosmic manna. This process starts high in the atmosphere, where ultraviolet radiation tears apart simple molecules like methane and carbon dioxide. The resulting fragments, highly reactive radicals, collide and link together into chains, growing heavier until they form microscopic tar-like particles. Experiments recreating these conditions produce astonishing results. When researchers simulate Titan's chemistry by irradiating methane-nitrogen mixtures, the lab fills with brownish haze containing thousands of different organic compounds, including amino acids and nucleotide bases. On young Earth, these particles wouldn't stay suspended forever. Like fine dust settling on furniture, they'd gradually drift downward, delivering concentrated organic payloads to lakes, oceans, and land. What makes atmospheric haze so intriguing is its ability to concentrate rare molecules. While other theories rely on localized events like lightning strikes or hydrothermal vents, hazes operate planet-wide, filtering and enriching organics through a natural distillation process. Some haze layers might even act as protective shields, absorbing harmful UV radiation below while allowing gentler wavelengths through, creating a Goldilocks zone where delicate molecules can form without being immediately destroyed. The parallels with Titan are striking. NASA Cassini mission detected massive molecules called polycyclic aromatic hydrocarbons in Titan's haze, the same class of compounds found in meteorites and implicated in life's origins. Even more remarkably, Titan's haze particles carry electrical charges, hinting at how they might have organized into more complex structures under Earth's different conditions. Critics question whether these atmospheric products could survive the descent to Earth's surface intact. But recent models show that while smaller molecules might burn up, larger haze aggregates could parachute down gently, especially if coated with protective ice layers. Some may have even skipped the plunge entirely, riding wind currents until washing out in rainfall, a scenario that would spread organic riches evenly across the planet. This theory expands life's possible birthplaces beyond surface environments. If hazes contributed significantly, then planets without oceans or volcanic activity might still brew life's ingredients aloft in their skies. Imagine exoplanets with permanent overcasts, their surfaces slowly being blanketed by organic snow worlds where life's story begins not in water or rock, but in the dim glow of a smog-filtered sun. The universe, it seems, has more than one recipe for cooking up complexity and sometimes the most unassuming processes. Like the slow settling of dust, hold the keys to existence itself. Beneath Earth's crust lies a hidden world of unimaginable pressure, a place where rocks flow like syrup and diamonds form from pure carbon. But what if this scorching, crushing environment did more than just create gemstones? Some scientists now propose that the deep mantle, far below the reach of sunlight or surface chemistry, could have been a crucible for life's first organic molecules. It's a radical idea that the building blocks of biology didn't just form on Earth's surface or in its oceans, but were forged in the seething darkness beneath our feet. The theory hinges on a surprising fact: Earth's mantle isn't just solid rock. Tiny pores and fractures within mantle minerals trap fluids rich in hydrogen, carbon, and nitrogen. Under the intense pressure of hundreds of miles of overlying rock, These simple molecules undergo dramatic transformations. Laboratory experiments using diamond anvil cells, devices that replicate mantle pressures, show methane and water can combine to form complex hydrocarbons even without oxygen or sunlight. Some studies suggest amino acids might emerge under these extreme conditions, their structures stabilized by the very pressure that would crush them at lower depths. But how could these deep Earth molecules ever reach the surface? The answer lies in Earth's restless geology. Subduction zones where tectonic plates dive back into the mantle don't just swallow material, they also exhale it. Volcanic arcs like the Ring of Fire act as planetary chimneys, belching gases from the depths. Hydrothermal vents connected to deep magma chambers might shuttle mantle-derived organics upward in superheated fluids. And then there are kimberlite pipes, narrow, explosive pathways that blast diamonds, and potentially their molecular hitchhickers from the mantle to the surface in geologic milliseconds. The evidence isn't just lab-based. In remote regions like Russia's Kamchatka Peninsula, scientists have discovered hydrocarbons emerging from volcanic gases molecules that couldn't have formed from surface life or conventional chemistry. Even more intriguing, some diamond inclusions contain microscopic pockets of fluid with organic signatures, perfectly preserved time capsules from the deep Earth. Critics raise valid concerns. Could fragile organic molecules survive the journey through molten rock? Proponents counter that certain mineral matrices might shield them, like microscopic armored cars. Others question whether mantle chemistry could produce enough organics to matter. But if even a fraction of Earth's vast subsurface contributed, it would dwarf surface reservoirs. This theory upends traditional thinking about life's origins. If true, it suggests planets don't need hospitable surfaces to brew life's ingredients. Their furnaces might be hiding below. Imagine icy moons like Europa or Enceladus, their rocky mantles squeezed by tidal forces, quietly assembling organics in the dark. The universe's recipe for life might not just be written in starlight or ocean tides, but in the slow, fiery breath of planets themselves. At the smallest scales of the universe, particles don't play by the rules we're used to. They cheat, vanishing through barriers that should be impossible to cross. This bizarre quantum quirk, called tunneling, might have been nature's secret shortcut for cooking up life's molecules in the frozen depths of space. While classical chemistry says reactions slow to a crawl in the interstellar chill, quantum mechanics whispers a different story, one where atoms pull impossible heists to jumpstart biology before planets even formed. Picture a hydrogen atom drifting near a speck of cosmic ice. Normally, the energy needed to bond with another atom would require heat, something in short supply at -260 degrees Celsius. But in the quantum realm, particles don't wait for permission. There's always a tiny chance the hydrogen will teleport through the energy barrier like a ghost walking through walls, enabling reactions that defy conventional chemistry. Lab experiments have clocked this phenomenon in action, showing certain organic molecules forming hundreds of times faster in space-like conditions than classical models predict. Enzymes in your body use similar tricks today, proving biology has no qualms about borrowing from quantum weirdness. The implications are staggering. Quantum tunneling could explain why telescopes detect complex organics in places thermodynamics says should be inert, like the frozen outskirts of protoplanetary disks or the surface of interstellar dust grains. Some calculations suggest tunneling might even favor the formation of specific molecular shapes, potentially skewing cosmic chemistry toward the configurations life eventually adopted. Imagine the universe's first biomolecules weren't just random products, but beneficiaries of a hidden quantum bias sculpting them toward usefulness. But here's where it gets wilder. Quantum effects aren't limited to single particles. Under the right conditions, entire molecules can become smeared out across multiple positions simultaneously through quantum superposition. Recent simulations show this delocalization might have allowed precursor molecules to explore countless reaction pathways in parallel, effectively conducting chemistry's equivalent of 1,000 lab experiments at once. The coldest regions of space could have been quantum playgrounds where the rules of probability conspired to fast-track complexity. Not everyone's convinced, of course. Critics argue that while tunneling explains simple reactions, bridging the gap to life's complexity requires more than quantum luck. Yet the same was once said about organic molecules existing in space at all until we found them everywhere from comets to nebulae. As detectors grow more sensitive, we're uncovering quantum fingerprints in cosmic chemistry that hint at a deeper layer of organization beneath the apparent chaos. This theory does more than add another origin story. It reshapes how we see the universe's creative potential. If quantum effects turbocharged prebiotic chemistry, then life's ingredients might be inevitable even in the most hostile environments. Frozen moons, interstellar clouds, even the thin atmospheres of rogue planets drifting between stars could all be running quantum chemistry experiments in slow motion right now. The coldest corners of creation might be hotbeds of quantum innovation, quietly assembling life's puzzle pieces one impossible reaction at a time. Earth's magnetic field is more than just a compass guide. It could have been an invisible hand shaping the very molecules that led to life. Picture our planet 4 billion years ago, its molten core churning violently, generating a magnetic field far stronger than today's. This field didn't just deflect solar winds, it might have acted like a cosmic organizer, aligning floating molecules in precise orientations that made certain chemical reactions not just possible but inevitable. The magic lies in a property called chirality, the idea that molecules can exist in mirror image forms like left and right hands. Life as we know it overwhelmingly prefers left-handed amino acids and right-handed sugars, a bias so consistent it can't be random. Magnetic fields offer a compelling explanation. When exposed to intense magnetism, certain molecules align like compass needles, subtly favoring one chiral form over another. Experiments with polarizing magnets have shown this effect in action, producing slight but measurable imbalances in amino acid solutions, echoes of the same preference seen in biology. But how could this play out on early Earth? The planet's surface was a cauldron of chemical soups, tidal pools, volcanic runoff, maybe even layers of primordial goo. As these mixtures swirled under the influence of Earth's magnetic field, chiral molecules might have gradually shifted toward uniformity. Think of it as nature's sorting hat, nudging molecules into alignment over millennia. Some researchers propose that crustal minerals like magnetite could have amplified this effect locally, creating hotspots where magnetic alignment turbocharged the selection process. The implications stretch beyond Earth. Exoplanets with strong magnetic fields might be more likely to develop life not just because they're shielded from radiation, but because their fields act as molecular choreographers. Mars, with its long-dead magnetic dynamo, could have lost more than atmospheric protection. It might have missed the chance to bias its chemistry toward life's preferred configurations. Meanwhile, Jupiter's moon Ganymede, the only moon with its own magnetic field, could be quietly aligning organic molecules beneath its icy crust right now. Critics point out gaps Earth's field might not have been strong enough to cause significant chirality on its own, but combine it with other forces like polarized sunlight or flowing water, and the effect could compound. Recent studies show that magnetized mineral surfaces, when subjected to cyclical wet-dry conditions, dramatically increase chiral selectivity. It's a reminder that life's origins likely weren't a single eureka moment, but a symphony of subtle influences working in concert. What makes this theory so elegant is its universality. Magnetic fields aren't rare, they're woven into the fabric of planets, stars, even galaxies. If they played a role in steering Earth's chemistry, then the same invisible forces could be quietly guiding molecules toward life across the cosmos, one aligned reaction at a time. Floating between the stars, smaller than a speck of sand yet vast on an atomic scale, cosmic dust grains might hold the answer to life's most puzzling question: how simple atoms morphed into complex molecules. These microscopic flecks of rock and ice scattered throughout galaxies are far from inert. Instead, they're the universe's tiniest laboratories where chemistry unfolds with eerie precision in the vacuum of space. Picture a single dust grain, its surface pitted and irregular, drifting through a molecular cloud. Like a magnet, it attracts hydrogen, carbon, and oxygen atoms that stick to its icy coating. Here, in the frozen stillness, something extraordinary happens. The grain's surface acts like a cosmic workbench, bringing atoms so close together that they overcome their natural reluctance to bond, nudged along by the faint whisper of starlight or the occasional zap from a cosmic ray. What makes these grains so special is their structure. Under a microscope, they resemble lumpy sponges, riddled with pores and ridges that create perfect nooks for molecules to nestle and react. Some grains contain silicate cores, while others are mantled in layers of frozen methane and ammonia, each type hosting different chemical reactions. Experiments mimicking these conditions reveal their astounding efficiency. When scientists recreate interstellar dust in vacuum chambers, they observe simple molecules like water and carbon monoxide transforming into complex organics, including precursors to sugars and amino acids. It's as if the grains are pre-programmed to assemble life's building blocks, patiently stacking atoms like a cosmic jigsaw puzzle. The real magic lies in their patience. On Earth, chemical reactions race forward, often burning out quickly. But in space, dust grains operate on a timescale of millennia. A single reaction might take thousands of years, with molecules waiting frozen until just the right amount of energy, from a passing photon or a glancing particle, tips them into bonding. This glacial pace has an unexpected advantage. It allows for near-perfect precision. Unlike chaotic earthly chemistry, where molecules collide haphazardly, dust grains offer controlled environments where reactions unfold with almost surgical accuracy. Telescopes have caught glimpses of this process in action. In the Orion Nebula, astronomers detected the sugar glycolaldehyde clinging to dust grains, while the Taurus molecular cloud revealed dust-coated acetic acid, a key ingredient in metabolism. But how do these space-forged molecules end up on planets? The answer lies in star formation. When a molecular cloud collapses to birth a new solar system, its dust grains become the raw material for comets, asteroids, and eventually planets. Heat from the young star vaporizes the grain's icy coatings, releasing their organic cargo into the swirling protoplanetary disk. Later, impacts and cosmic deliveries ferry these molecules to planetary surfaces. Imagine a comet packed with dust grain organics splashing into Earth's early oceans. A single such impact could have delivered more prebiotic material than all of Earth's primordial soups combined. The implications stretch beyond our solar system. If dust grains are universal chemists, then the ingredients for life aren't rare treasures, they're as common as starlight. Every newborn planet might inherit a starter kit of organics pre-assembled in the void. Even now, in the dark clouds between stars, countless grains are quietly assembling molecules that could one day awaken as life. It's a humbling thought that the universe's smallest specks might be its most prolific architects, weaving complexity from cosmic nothingness one atom at a time. What if the universe's first organic molecules were cooked up like a cosmic pizza? Meet the prebiotic pizza hypothesis, a theory that sounds almost too playful to be real until you consider the science behind it. The idea revolves around heated mineral surfaces, nature's version of a stovetop, where simple molecules could have gathered, concentrated, and transformed under just the right conditions. Imagine a volcanic plain billions of years ago, its rocky surfaces baked by geothermal heat. Water rich in dissolved chemicals seeps into cracks and pores, then evaporates, leaving behind a concentrated residue of organics. Now repeat this cycle endlessly like a molecular conveyor belt, and you've got a recipe for complexity. The brilliance of this theory lies in its simplicity. Just as a pizza's toppings caramelize and fuse under heat, mineral surfaces like basalt or iron oxides could have provided the perfect pan for prebiotic chemistry. These materials aren't passive, they're chemically active, with tiny imperfections and charged spots that act like molecular Velcro, grabbing and holding ingredients in place. Lab experiments show that when amino acids or sugars land on heated minerals, they don't just sit there. They link up, forming chains that might eventually resemble proteins or RNA. The process even has a built-in quality control system. Weaker bonds break under the heat while stronger ones persist, creating a natural filter for stable structures. But why call it a pizza? The analogy goes deeper than whimsy. Like a well-topped pie, the key is layering. Minerals accumulate thin films of organic material, then heat drives reactions between those layers. Some models suggest that tidal zones or geyser fields could have created alternating wet and dry phases, spreading the molecular sauce, then baking it over and over. The result, a slow but steady buildup of complexity, one sizzling cycle at a time. The prebiotic pizza hypothesis isn't just a fun thought experiment, it's backed by hard data. In 2019, researchers demonstrated that heated iron-rich minerals could catalyze the formation of peptide bonds, the same links that hold proteins together in your body. Even more compelling, these reactions work best at temperatures around 80 degrees Celsius, similar to a bubbling hot spring or a sun-scorched rock pool. And unlike lightning or radiation, which deliver energy in violent bursts, geothermal heat provides a steady, gentle push, allowing delicate molecules to assemble without being shredded. Critics might dismiss the idea as too niche, arguing that localized hotspots couldn't produce enough organics to matter globally. But consider this: Earth's early crust was far more volcanic than today, riddled with geothermal features. A single active region could have hosted countless microenvironments, each churning out batches of prebiotic material like a cosmic pizzeria. Scale that up across millions of years, and suddenly the numbers start to make sense. The bigger picture here is deliciously subversive. If life's building blocks could emerge from something as mundane as heated rocks, then the universe might not need exotic conditions to cook up biology, just patience, the right ingredients, and a little bit of heat. It's a reminder that sometimes the most profound mysteries have answers hiding in plain sight, sizzling away like a forgotten slice on a stovetop, and who knows? Maybe right now, on some distant moon with geothermal vents, the universe is still baking its next great experiment, one molecular pizza at a time. Among the swirling chaos of early Earth's chemistry, one molecule stands out as a potential linchpin: RNA. The RNA world hypothesis suggests that before DNA or proteins, this versatile molecule might have been life's original architect, carrying genetic information and catalyzing reactions all on its own. But here's the mystery: how did RNA's precise building blocks, nucleotides, emerge from the primordial soup of simple organics? The answer could lie in the very theories we've explored, woven together into a chemical tapestry that transforms chaos into coded complexity. Take the amino acids forged in miller-urey's lightning-filled flasks or the nucleobases detected in meteorites. These molecules aren't just random products, they're potential stepping stones to RNA. Picture a volcanic shoreline where tidal cycles concentrate hydrogen cyanide, a simple compound abundant in space and early Earth. Under the right conditions, this toxic chemical can undergo a cascade of reactions, forming adenine, one of RNA's 4 key letters. Lab experiments have recreated this process, showing how ultraviolet light or geothermal heat can stitch hydrogen cyanide into nucleobases with startling efficiency. It's as if the universe had a hidden blueprint, nudging simple molecules toward biological relevance. But nucleobases are only half the story. RNA's backbone, a twisting ladder of sugar and phosphate, poses its own puzzle. Ribose RNA sugar is notoriously fragile, decomposing rapidly in water. Yet recent work reveals a surprising solution. Minerals like borate can stabilize ribose, locking it into place long enough to bond with nucleobases. Imagine hot springs laced with borate-rich clays, their waters acting as molecular matchmakers. Here, the sugar's fragility becomes an advantage. Only the sturdiest configurations survive, naturally selecting the structures that eventually dominate biology. The final piece, phosphates, often dismissed as too scarce to matter. Yet hydrothermal vents spew phosphate-rich fluids, and volcanic rocks can release phosphorus when weathered. Even more intriguing, certain meteorites contain phosphides, minerals that react with water to form phosphates. This cosmic connection suggests RNA's backbone might have been assembled from both terrestrial and extraterrestrial ingredients, a cocktail shaken by geology and delivered by comets. What ties these threads together is their convergence in real-world conditions. In 2016, researchers demonstrated that wet-dry cycling, like that in tidal pools or geothermal fields, could fuse nucleobases, ribose, and phosphates into complete nucleotides. The process mirrors earlier theories. Cosmic rays or electric sparks create the parts, mineral surfaces assemble them, and environmental cycles refine the product. It's a symphony of chance and necessity, where chemistry's randomness gets funneled into biological precision. The RNA world hypothesis gains even more traction when you consider RNA's dual talents. Unlike DNA, which merely stores information, RNA can fold into intricate shapes that catalyze reactions, a relic, perhaps, of a time when molecules had to be both blueprints and builders. Some ribozymes, RNA's enzymatic cousins, can even replicate snippets of genetic code, hinting at how a molecule might bootstrap its own evolution, yet puzzles remain. Could fragile RNA chains have endured Earth's violent youth? Some answers come from extremophiles, modern microbes thriving in acidic hot springs or Antarctic ice. Their existence proves that nucleic acids can withstand harsh conditions, especially when sheltered by minerals or lipids. Others point to simpler proto-RNAs, molecules with stripped-down backbones that might have preceded the full version. This theory doesn't just connect organic chemistry to biology, it bridges the animate and inanimate. If nucleotides form through processes as universal as cosmic radiation, hydrothermal chemistry, and tidal cycling, then RNA's rise might not be an earthly fluke but a cosmic imperative. Planets with similar geology and energy sources could have followed the same chemical breadcrumbs, their molecular experiments echoing ours. The universe, it seems, doesn't just build organic molecules, it conspires to make them matter. Deep beneath Earth's ancient oceans, in places where pressure bends the rules of chemistry, lies a state of matter so strange it defies ordinary classification: supercritical carbon dioxide. Picture a substance that's neither fully gas nor liquid, but a hybrid with the penetrating power of a gas and the dissolving ability of a liquid. In this exotic phase, carbon dioxide becomes something more. A universal solvent capable of facilitating reactions that would stall in normal conditions. Scientists now believe supercritical CO2 could have been the universe's stealthy alchemist, bridging the gap between simple molecules and life's complex precursors under the crushing weight of hydrothermal vents or subterranean depth. What makes supercritical CO2 so special is its duality. At temperatures above 31 degrees Celsius and pressures 73 times Earth's surface level, conditions common in the planet's crust and near deep sea vents, CO2 enters this fluid limbo. Here, its molecules gain freakish mobility, slipping through microscopic pores in rocks like ghosts, while still packing enough punch to dissolve organic compounds that would resist water. Experiments simulating these environments reveal astonishing results. When formic acid, a simple molecule found in comets, meets supercritical CO2 under vent-like pressures, it can undergo reactions that produce peptides, the chains that form proteins. Even more striking, these reactions happen without the metal catalysts required in water, suggesting CO2 might have offered a parallel pathway to complexity. The implications ripple outward. Hydrothermal vents, already prime candidates for life's origins, take on new dimensions when you factor in supercritical CO2. Imagine a vent's labyrinthine mineral structure flooded with this reactive fluid, its pores acting as countless nanoreactors where dissolved organics link up under pressure. Unlike water, which can hydrolyze and break apart delicate molecules, CO2's gentler touch might have allowed fragile chains to grow uninterrupted. Some researchers compare it to a molecular loom, weaving threads of carbon into ever-lengthening strands. But the real surprise is how this process mirrors modern biology. Supercritical CO2 behavior eerily resembles enzymes in living cells. Both create microenvironments where reactions proceed with impossible efficiency. Today, industries exploit supercritical CO2 to manufacture pharmaceuticals and extract delicate compounds without damaging them. It's poetic to think nature might have used the same trick billions of years earlier, crafting life's ingredients in planetary pressure cookers before life even existed. The theory gains credence from recent discoveries. In the Lost City hydrothermal field, a vent system in the Atlantic, scientists detected organic synthesis occurring in CO2-rich zones, with molecules forming at rates unseen in normal seawater. Meanwhile, lab studies show supercritical CO2 can selectively concentrate certain amino acids, effectively sorting the molecular wheat from the chaff. This selectivity is crucial. Life doesn't just need any organics, but specific configurations capable of precise interactions. Of course, mysteries linger. Could supercritical CO2 have produced enough material to matter on a planetary scale? And how would these molecules transition to water-based systems once life emerged? Proponents suggest tectonic activity might have released trapped CO2 reservoirs in episodic bursts, flooding coastal zones with prebiotic riches. Others point to lipid-like molecules that spontaneously form membranes in CO2-water interfaces, creating natural bridges between the two realms. This theory does more than add another scenario. It redefines our chemical imagination. If supercritical CO2 played a role, then life's cradle might extend beyond sunlit ponds or volcanic vents to the pressurized depths we've barely explored. Even now, beneath the icy shells of moons like Enceladus or in the subsurface oceans of exoplanets, similar reactions could be unfolding in the dark, proving once again that life's recipe book is written in more than just water and light. Deep in the emptiness between stars, where darkness seems absolute, a hidden force might have nudged the universe toward life. It's not gravity or magnetism, it's light, but not as we normally see it. Circularly polarized starlight, a twisted form of electromagnetic radiation where the wave spirals like a corkscrew through space, could have played puppet master with the earliest organic molecules, subtly favoring the shapes that life would later adopt. This isn't just light, it's light with a bias, and that bias might explain one of biology's deepest mysteries: why life overwhelmingly uses molecules with specific handedness. Take amino acids, the building blocks of proteins. In nature, they almost exclusively appear in their left-handed form, while sugars in DNA are right-handed. This uniformity, called homochirality, can't be random. Something must have tipped the scales. Polarized starlight offers an elegant solution. When this spiraling light interacts with molecules in space, it doesn't treat both mirror image forms equally. Just as a corkscrew only turns one way, the light preferentially destroys or alters one chiral form over the other. Over millions of years, this slow filtration could have skewed the molecular inventory of entire molecular clouds, embedding a cosmic preference into the raw materials of planets. The evidence comes from both space and lab. In the Orion Nebula, astronomers detected an excess of circularly polarized light near star-forming regions, exactly where complex organics are known to exist. Back on Earth, experiments recreating these conditions show eerie results. Shine circularly polarized ultraviolet light on a racemic mixture, equal parts left and right-handed molecules, and one form begins to dominate. In some trials, the imbalance reaches up to 10%, a huge bias by cosmic standards. Even more compelling, meteorites like Murchison carry amino acids with slight chiral excesses, as if pre-screened by some universal filter before delivery to Earth. But how could something as delicate as a light wave leave such a lasting mark? The secret lies in amplification. A slight initial bias, whether from polarized light or another source, could have snowballed through chemical cascades. Imagine a molecule slightly favoring one form catalyzing reactions that produce more of the same, creating a runaway feedback loop. This chiral amplification turns a nudge into a shove, something researchers have demonstrated in lab simulations of prebiotic chemistry. Once started, the process might have been unstoppable, locking in life's handedness long before the first cell formed. The implications stretch beyond Earth. If polarized light is a universal sculptor, then exoplanets bathed in similar radiation from their host stars might inherit the same molecular preferences. We could even search for this signature in distant systems. Detecting an excess of one chiral form in a planet's atmosphere might hint at not just the presence of organics, but organics already primed for life. It's a humbling thought. The same light that paints the cosmos in color might also be quietly steering its chemistry toward complexity, one twisted photon at a time. Geothermal fields aren't just steamy landscapes, they're nature's grand chemistry experiments, where temperature gradients create perfect conditions for molecules to evolve through relentless cycling. Picture a prehistoric hot spring system, its waters ranging from near boiling at the vent's mouth to lukewarm at the edges. These zones aren't static, they pulse like a living organism as underground heat sources fluctuate. Each temperature band becomes a specialized reactor, subjecting molecules to different energies that push them through transformative cycles. In the scorching heart of the spring, simple compounds break apart into reactive fragments. As these fragments drift toward cooler regions, they recombine into new configurations, some stable, others fleeting. Then, when geothermal activity shifts, the current sweeps everything back toward the heat, restarting the process. It's evolution in fast forward, with countless molecular generations rising and falling like tides. Lab experiments reveal the power of these gradients. When scientists simulate geothermal cycling by alternately heating and cooling chemical mixtures, they observe something astonishing. Molecules don't just react randomly, they march toward complexity. Amino acids form vesicles that protect themselves from disintegration during heat phases. Nucleobases link into chains only in precise temperature windows, then get preserved when flushed to safer zones. What seems like chaos is actually a sophisticated sorting mechanism, where only the most resilient structures survive multiple rounds. The system even mimics natural selection at the molecular level. Heat acts as the predator, weeding out weak bonds, while cooler areas become nurseries for the survivors to propagate. Real-world geothermal sites add compelling evidence. New Zealand's Champagne Pool, with its 90-degree thermal gradations, hosts microbial communities precisely stratified by temperature tolerance. Nearby, silica terraces preserve microscopic fossils of ancient heat-loving organisms, suggesting such environments have long been crucibles for biological innovation. Even more telling are the mineral deposits, layers of iron sulfides and clays that could have acted as both catalysts and archives, recording eons of chemical experimentation in their crystalline structures. But here's the twist that makes geothermal gradients universal contenders. They're self-sustaining and scalable. A single system can operate for millennia without external input, powered solely by Earth's internal heat. The gradients also create countless microenvironments. Each pore in surrounding rocks becomes a miniature lab where slightly different conditions test alternative molecular strategies. When you scale this up across thousands of springs spanning continents, the probability of rare but crucial reactions skyrockets. It's like the universe built a planetary-scale testing facility, running trillions of parallel experiments simultaneously. Critics often ask how delicate organics could endure such extreme cycling. The answer lies in the gradient's gradual transitions. Unlike sudden shocks from lightning or impacts, geothermal shifts happen over hours or days, giving molecules time to adapt. Some theorize lipid-like molecules may have formed protective coatings early on, creating protocells that turn the system's volatility into an advantage. Others point to mineral surfaces that anchor molecules during turbulent phases, acting like molecular life rafts. What emerges is a vision of Earth as a natural supercomputer, with geothermal fields processing chemical information through endless loops of destruction and renewal. And if this happened here, why not on Mars' ancient Tharsis bulge, where colossal volcanoes once fed vast hot spring networks? Or beneath the ice of Enceladus, where hydrothermal vents might still be churning today? The universe seems to have a fondness for turning heat differentials into engines of creativity, whether in stars, planetary cores, or these unassuming bubbling pools where temperature itself became the unseen hand guiding matter toward life. Comets are more than just dirty snowballs. They might be cosmic chemistry sets, their frozen interiors hiding the products of a radiation-driven alchemy that predates our solar system. Picture a comet's nucleus, a dark, icy body drifting in the deep freeze of space. On its surface, temperatures hover near absolute zero, but this isn't a dormant landscape. Bombarded by ultraviolet light from distant stars and peppered with cosmic rays, the comet's simple ices water, methane, ammonia undergo a metamorphosis. Every photon or high-energy particle that slams into these frozen molecules doesn't just bounce off. It kickstarts a reaction, breaking bonds and forging new ones in the frigid vacuum. What emerges isn't just random debris, but a menagerie of complex organics, some strikingly similar to the building blocks of life. Laboratory experiments have brought this process to life. Scientists recreate comet-like conditions by freezing mixtures of water, methanol, and ammonia in vacuum chambers, then blasting them with UV radiation or proton beams to simulate cosmic rays. The results are staggering. Within hours, the colorless ice turns yellow, then ruddy brown, a visual signature of complex organics forming. Analyze that ice and you'll find glycine, the simplest amino acid, alongside adenine, a key component of DNA. Some experiments even detect sugar-like molecules and amphiphiles, compounds that naturally self-assemble into membrane-like structures. It's as if radiation acts as a cosmic chef, taking the blandest ingredients and transforming them into a molecular feast. One of the most compelling studies came from the University of Hawaii, where researchers irradiated icy mixtures similar to those found in the interstellar medium. Not only did they produce amino acids, but they also observed something eerie. The molecules showed a slight chiral imbalance, mirroring the preference for left-handed amino acids seen in terrestrial life. This hints that the universe might have been pre-biasing chemistry toward biological relevance long before planets formed. Even more astonishing, when warmed to simulate a comet approaching the sun, these organics didn't break down. They linked into longer chains, as if the comet itself was finishing the recipe. The implications ripple outward. Space telescopes have detected organic-rich ices in protoplanetary disks and molecular clouds, suggesting this process isn't rare, it's universal. When comets like 67P/Churyumov-Gerasimenko were sampled by missions like Rosetta, they carried not just water but formaldehyde and hydrogen cyanide, precursors to even more complex molecules. And because comets are essentially time capsules from the solar system's birth, their chemistry offers a snapshot of the raw materials available when planets and potentially life were taking shape. But here's the twist: cometary ice irradiation doesn't just explain how organics form, it also solves the delivery problem. A single comet impacting early Earth could have deposited billions of tons of pre-processed organics, effectively seeding the planet with a starter kit for life's chemistry. Experiments at the University of California, Berkeley, showed that when comet-like ice analogs were subjected to impact simulations, up to 20% of the organics survived the collision, intact and ready to mingle with Earth's primordial soups. Critics argue that radiation is as much a destroyer as a creator, and they're not wrong. Cosmic rays can shatter molecules as easily as they assemble them. Yet that's where the ice itself becomes a protagonist. Frozen matrices act like molecular shields, absorbing destructive energy while allowing constructive reactions to proceed in their crystalline cages. Over millions of years, the balance tips toward synthesis, with the hardiest molecules accumulating like cosmic fine wine. This theory reshapes how we see comets, not as inert relics, but as active participants in the story of life. Their icy interiors, forged in the radiation baths of interstellar space, might have been the universe's first laboratories, quietly perfecting recipes that would later be served on planetary platters. And if that's true, then every comet streaking through our skies today isn't just a spectacle, it's a reminder of the deep, radiant connections between the cosmos and the chemistry that became us. On Titan, Saturn's enigmatic moon, rivers of liquid methane carve valleys into icy landscapes, pooling into vast hydrocarbon seas that shimmer under the dim orange haze. These alien bodies, Kraken Mare, Ligeia Mare, aren't just geological oddities. They could be laboratories for a form of chemistry we've barely imagined. At the boundaries where different hydrocarbon liquids meet, methane mingling with ethane, or benzene dissolving in nitrogen-rich flows, unique reactions might unfold, stitching simple molecules into the kind of complexity that could pave the way for life. Unlike Earth's water-based chemistry, where polar molecules dominate, Titan's hydrocarbon solvent system operates under different rules. Here, nonpolar compounds dissolve readily, and temperature swings as low as -180 degrees Celsius slow reactions to a glacial pace, but that doesn't mean they stop. Lab simulations reveal the unexpected fertility of these liquid frontiers. When scientists recreate Titan's conditions by chilling methane and ethane mixtures, then introduce trace compounds like hydrogen cyanide or acetylene, something remarkable happens. Over weeks or months, these mixtures produce long-chain hydrocarbons and even cyclic compounds resembling the aromatic structures found in DNA. The secret lies in the interfaces where two liquids meet. Their slight differences in polarity and density create microenvironments ripe for reactivity. Ethane-rich layers might act as reservoirs, holding dissolved organics stable, while methane-dominated zones could shuttle reactants to these boundary regions, where gentle thermal currents or seasonal evaporation cycles concentrate them. It's a slow dance, but given Titan's billion-year timescales, the results could be profound. The Cassini mission added fuel to this theory when it detected vinyl cyanide in Titan's atmosphere, a molecule capable of forming stable membranes in liquid methane, akin to how lipids assemble in water. Imagine microscopic vesicles bobbing at the edges of Titan's lakes, their surfaces organizing organic molecules into ordered arrays. These structures wouldn't resemble Earth cells, but they might serve a similar purpose: compartmentalization, the first step toward complexity. Even more intriguing, Titan's weather cycles could amplify this process. Seasonal rains wash atmospheric organics into the seas, while evaporation leaves behind concentrated residues at the shorelines, nature's version of a prebiotic distillation apparatus. Critics argue that Titan's cold cripples chemistry too severely for meaningful progress. Yet recent experiments at the University of Western Ontario tell a different story. By simulating tidal sloshing in hydrocarbon seas, researchers observed how mechanical energy, waves or currents, could compensate for the lack of heat, bringing reactants together with enough force to overcome the cold's inertia. Add to this the occasional cryovolcanic eruption, spewing warmer mixtures into the seas, and you have a system capable of punctuated leaps in complexity. What makes Titan's hydrocarbon boundaries so compelling is their sheer novelty. They force us to redefine what habitable means. If organic synthesis can thrive in liquid methane at cryogenic temperatures, then why not on exoplanets with hydrocarbon oceans orbiting red dwarfs, or in the subsurface reservoirs of distant ice moons? The universe, it seems, has a flair for turning even the most alien environments into stages for chemistry's greatest hits, each act playing out under rules we're only beginning to decode. Deep within Earth's ancient rocks, hidden in the intricate lattices of crystals, lies a code written not in nucleotides but in atoms, a geometric language that might have guided life's earliest molecular assemblies. The mineral surface coding theory proposes that the regular, repeating patterns of certain minerals acted like molecular blueprints, aligning organic compounds into precise arrangements that eventually gave rise to self-replicating systems. Picture the face of a pyrite crystal, its cubic symmetry forming a grid of iron and sulfur atoms. To the naked eye, it's just a shiny rock, but on a microscopic scale, those orderly rows could have served as nature's first template, forcing floating molecules to line up in ways that encouraged bonding and complexity. This isn't just speculative. Lab experiments have demonstrated the eerie efficiency of mineral surfaces as molecular organizers. Take clay minerals like montmorillonite, whose layered structures create vast charged surfaces. When scientists introduce simple nucleotides to these clays under prebiotic conditions, something remarkable happens. The minerals don't just passively host the molecules, they actively shepherd them into chains resembling RNA. The clay's negative charges hold the nucleotides in place while its rhythmic grooves provide the spacing needed for polymerization. It's as if the mineral's atomic geometry was preordained to coax chaos into order. Even more striking, some crystals exhibit chiral preferences, subtly favoring one molecular orientation over its mirror image, a potential explanation for life's universal handedness. The theory gains depth when you consider how minerals could have gone beyond mere assembly to enable replication. Certain sulfides, like zinc blende, contain defects in their crystal lattices, tiny imperfections that create pockets of unexpected chemistry. These defects might have acted as catalytic hotspots, not just linking molecules but also facilitating their duplication. Imagine a mineral surface where a newly formed RNA strand peels away, leaving behind a negative space perfectly shaped to guide the synthesis of its complement. Over time, this mineral-mediated copying could have transitioned to standalone replication, with the crystal's role fading as biology took over. Real-world evidence comes from some of Earth's oldest rocks. In the Pilbara Craton of Australia, mineral deposits dating back 3.5 billion years preserve textures suggestive of organic mineral interactions. Similarly, lab-grown pyrite crystals exposed to hydrogen sulfide and iron, common components of early Earth's hydrothermal systems, spontaneously develop porous microstructures that could have housed and protected delicate molecular chains. These findings hint that mineral coding wasn't a rare fluke, but a widespread phenomenon tied to planetary geology itself. Critics rightly point out gaps. How, for instance, did mineral-bound systems transition to free-floating biology? One compelling answer lies in lipids, fatty acids which self-assemble into cell-like vesicles, readily coat mineral surfaces in experiments, eventually pinching off to encapsulate mineral-bound molecules. This could have created a bridge between mineral templates and true cells, with the rocks effectively midwifing the first protocells into existence. The implications stretch far beyond Earth. Mars's clay-rich regions, or the icy crusts of Europa and Enceladus, where mineral-water interactions abound, might harbor similar templates frozen in time. If mineral surfaces truly hold this coding potential, then the universe's path to life could be less about random chance and more about the inevitable marriage of geology and chemistry, a dance of atoms choreographed by crystals, waiting only for the right conditions to spring into motion. The skies above early Earth weren't just a passive backdrop, they crackled with invisible layers of electric potential, a hidden power grid that might have jump-started life's chemistry in ways we're only beginning to understand. Picture the atmosphere not as a uniform blanket, but as a towering layer cake of alternating charges, where positive and negative regions stack like celestial batteries. These gradients didn't just produce lightning, they created something far more subtle and widespread. A network of gentle but persistent energy sources perfect for coaxing delicate organic reactions without the destructive fury of storms. At the heart of this theory lies a phenomenon still visible today: modern thunderstorms separate charges on a massive scale, with ice crystals and water droplets colliding to create positive charges near the cloud tops and negative charges below. But on primordial Earth, with its thicker atmosphere and relentless volcanic activity, this separation might have occurred even in clear skies, forming vast horizontal strata of charged particles. Imagine wandering beneath such a sky. While no visible bolts split the air, the atmosphere itself would hum with potential, every gust of wind or dust devil stirring up localized pockets of energy. Laboratory experiments reveal how potent these quiet electric fields could be. When researchers expose simple gas mixtures, water vapor, nitrogen, carbon dioxide, to vertical electric gradients mimicking early atmospheric layers, something fascinating happens. Amino acids like glycine form at rates comparable to lightning experiments, but with a crucial difference: the products are more diverse and less fragmented. Unlike a lightning bolt's brute force approach, layered charge separation works like a precision tool, selectively energizing certain molecular bonds while leaving others intact. This selectivity matters. Life's building blocks need stability as much as they need energy, and atmospheric gradients could have provided both. The real magic happens at boundaries between charge zones. Where positive and negative layers meet, ions cluster into what physicists call electrosprays, microscopic regions of intense reactivity. These hotspots, though tiny, would have been ubiquitous, transforming the entire sky into a three-dimensional chemical reactor. Models suggest that over millennia, wind patterns could have concentrated organic products in specific regions, like high-altitude ice clouds or low-lying mist banks, creating natural collection points for prebiotic material. Supporting evidence comes from an unexpected place: Jupiter's cloud decks. NASA Juno spacecraft detected persistent charge separation in the gas giant's upper atmosphere, with organic molecules concentrating at interfacial boundaries. If this process occurs on worlds without surface oceans or volcanic activity, it suggests charge-driven chemistry might be a universal pathway. Even more telling are experiments showing that such electric fields can induce chiral preferences in amino acids, a potential explanation for life's mysterious handedness. Of course, puzzles remain. How would these sky-forged molecules safely descend to Earth's surface? Some propose they hitched rides on dust particles or rained down during gentle precipitation events, avoiding the destructive inferno of lightning strikes. Others suggest they accumulated in high-altitude ice crystals, eventually falling as organic, rich snow. Regardless of the delivery mechanism, the implications are profound. If atmospheric charge separation contributed significantly, then planets with active weather systems, regardless of temperature or composition, might universally trend toward organic complexity. This theory rewires our understanding of energy's role in life's origins. No longer confined to volcanoes or lightning bolts, the spark of creation might have flickered throughout the entire sky, a diffuse but omnipresent driver turning simple gases into life's precursors, one charged particle at a time. And if that's true, then the air we breathe today carries echoes of that ancient electric whisper, the same forces that once assembled life's puzzle still crackling in every cloud, every breeze, every fleeting spark between earth and sky. Among the most exotic theories about life's molecular origins lies an idea ripped straight from the fabric of spacetime itself: cosmic strings. These hypothetical flaws in the universe's structure, thinner than an atom yet denser than a neutron star, might have twisted the very laws of physics in their vicinity, creating bizarre pockets where chemistry behaved unlike anything we know. Imagine ribbons of pure energy left over from the Big Bang, stretching across light years like cracks in frozen ice, their gravitational shadows warping the quantum fields around them into unrecognizable shapes. In these distorted zones, the symmetry-breaking forces that normally dictate how particles interact could have flickered like candlelight, allowing normally impossible molecular arrangements to briefly flicker into existence. The math behind this is shockingly robust. Cosmic strings, if they exist, would be topological defects, kinks in spacetime's geometry so stable they could persist for billions of years. Theoretical models show their immense gravity would create anisotropic zones where fundamental constants like the electromagnetic coupling strength or even the electron mass might vary minutely along different axes. To atoms and molecules drifting into these regions, it would feel like the rules of chemistry had been rewritten overnight. Reactions prohibited by standard quantum mechanics could suddenly proceed, while mundane bonds might unravel without warning. Some calculations suggest amino acids could form chiral purity near cosmic strings, their mirror image versions suppressed by the skewed physics. Others propose these strings acted as cosmic conveyor belts, herding interstellar molecules into dense filaments where collisions and reactions multiplied. Evidence for this wild idea is circumstantial but tantalizing. Astronomers have observed mysterious gravitational lensing effects where no visible mass exists, one possible signature of cosmic strings bending light. Even more intriguing are the so-called dark flows, vast streams of galaxy clusters moving in unison toward unseen attractors, which some theorists argue could betray the presence of these spacetime scars. While no direct detection exists, the fact that cosmological models predict strings should have formed in the early universe lends the idea a veneer of plausibility. The implications for prebiotic chemistry are staggering. If a cosmic string passed through a molecular cloud, its distorted physics might have seeded that region with organic anomalies, molecules exhibiting handedness, unusual stability, or catalytic properties not seen elsewhere. When these clouds later collapsed into star systems, planets forming in their wake could have inherited these quirks as a head start toward biology. It's a cosmic version of loading the dice, where spacetime itself tilted the odds in favor of life's unlikely chemistry. Critics rightly point out the speculative nature of these ideas. Without empirical proof of cosmic strings, the theory remains in the realm of beautiful mathematics. Yet it serves a vital purpose, stretching our imagination about how many paths the universe might have taken to forge life's ingredients. After all, if defects in spacetime can influence galaxy formation, why not molecular assembly? The universe has never been shy about repurposing its grandest phenomena for the most delicate tasks. What makes this concept so captivating is its audacious bridging of scales. A phenomenon born in the first trillionth of a second after the Big Bang, spanning galactic distances, might have left fingerprints on the molecular machinery inside every cell of your body. It's a reminder that the story of life's origins isn't written solely in test tubes or tidal pools, but perhaps also in the hidden fractures of reality itself, where the cosmos occasionally bends its own rules to nudge chaos toward meaning. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most extreme chemistry labs. Picture the swirling maelstrom of an accretion disk, where superheated gas spirals toward oblivion at nearly light speed. Temperatures here soar to millions of degrees, pressures crush atoms into exotic states, and magnetic fields twist space itself into knots. It's the last place you'd expect delicate organic molecules to survive, let alone form. Yet some radical theories suggest these violent environments could be factories for life's building blocks, forging complexity in the crucible of chaos. The key lies in the accretion disk's layered structure. While the inner regions near the event horizon are hellishly hot, outer zones can be surprisingly temperate, comparatively speaking. At distances where temperatures drop below a few thousand degrees, carbon and nitrogen atoms ripped from doomed stars begin recombining in the turbulent plasma. Simulations show that under these conditions, simple molecules like carbon monoxide and hydrogen cyanide can persist long enough to undergo further reactions. The disk's insane rotation speeds act like a centrifuge, sorting molecules by mass and creating concentrated pockets where chemistry defies expectations. Even more counterintuitive is the role of radiation. The intense X-rays and gamma rays flooding these disks don't just destroy, they energize. When these high-energy photons slam into molecular fragments, they can catalyze the formation of more complex structures. Lab experiments using particle accelerators to mimic black hole radiation have observed amino acid precursors forming in these punishing conditions. It's as if the universe found a way to weaponize chaos, turning destruction into creation with each particle collision. The real wild card, quantum effects near the event horizon. Some models suggest that space-time distortions could temporarily stabilize otherwise impossible molecular configurations. Imagine a carbon chain stretched by tidal forces into an unnatural shape, just long enough for a rare reaction to occur before snapping back to normal. These fleeting moments might allow the synthesis of molecules that couldn't form anywhere else in the universe. Support for this theory comes from an unexpected place: quasar spectra. These ultra-bright black hole beacons sometimes show absorption lines matching complex organic molecules like polycyclic aromatic hydrocarbons. While skeptics argue these could be contaminants from foreground gas, others see them as fingerprints of chemistry happening right in the maelstrom. If confirmed, it would mean black holes aren't just endpoints for matter, but possibly way stations in its transformation toward complexity. The implications rewrite the rules of astrochemistry. If even a fraction of the organics forged in accretion disks escape via jets or winds, they could seed entire galaxies with prebiotic material. Picture a supermassive black hole's outflow spraying enriched matter across star-forming regions, a cosmic gardener planting seeds for future life. This might explain why we find complex organics in meteorites and interstellar clouds. They're not anomalies, but inevitable products of the universe's most energetic processes. Of course, the challenges are astronomical. Could any molecule survive the trip from an accretion disk to the cold reaches where planets form? Some researchers propose that hardy compounds might hitch rides on dust grains ejected at relativistic speeds, their structures preserved by the very forces that should tear them apart. Others suggest that black hole chemistry favors ultra-stable configurations, molecules pre-selected for resilience by the harshest environment imaginable. This theory doesn't just stretch our understanding of organic chemistry, it bends it until it breaks, then reforms it into something new. If proven, it would mean life's ingredients aren't just forged in the gentle nurseries of molecular clouds or the steady churn of planetary surfaces, but also in the most violent crucibles the cosmos can muster. The same forces that rip stars apart might secretly be assembling the pieces for what comes next, an echo of creation whispered in the roar of annihilation. Perhaps the ultimate irony, the darkest places in the universe could be hiding the brightest sparks of life's potential. And if that's true, then every supermassive black hole at a galaxy's heart might be more than a destroyer. It could be a silent architect weaving complexity from the threads of entropy itself. At the very edge of scientific speculation lies a theory so audacious it challenges our fundamental understanding of reality, that the universe's quantum vacuum isn't empty, but a seething foam of potential where particles flicker in and out of existence so fast we can't detect them. These quantum fluctuations, once thought to be mere background noise, might have played director in life's molecular theater, orchestrating improbable chemical reactions through sheer statistical inevitability. Imagine the quantum foam as a cosmic casino where trillions of subatomic bets are placed every second. Most cancel out, but occasionally, against impossible odds, the universe rolls a perfect hand. The math behind this is mind-bending yet elegant. In quantum field theory, so-called virtual particles constantly emerge in particle-antiparticle pairs, borrowing energy from the vacuum before annihilating almost instantly. But at the Planck scale, the smallest measurable unit of spacetime, these fleeting events create microscopic regions of distorted physics. For molecules floating in the primordial soup, these fleeting quantum blips could have acted like invisible fingers, momentarily tweaking reaction probabilities just enough to tip the scales toward complexity. An amino acid that should have broken apart might instead stabilize. A chance molecular collision could suddenly become inevitable. Lab experiments give tantalizing hints this isn't pure fantasy. When scientists trap molecules in electromagnetic fields and cool them near absolute zero conditions that minimize thermal noise, quantum effects begin dominating chemical behavior. Reactions occur at distances classical physics says are impossible, as if particles tunnel through barriers. Some researchers argue Earth's early crust, peppered with radioactive minerals emitting quantum-scale energy bursts, could have created similar hotspots where vacuum fluctuations became chemically significant. The wildest implication, quantum fluctuations might explain life's stubborn homochirality. Virtual particles lack mirror symmetry at fundamental levels, a property called parity violation. Over eons, this subtle bias could have snowballed through molecular networks, amplifying quantum randomness into biological certainty. It's as if the universe's smallest asymmetries wrote themselves into life's blueprint. Of course, skepticism abounds. Critics argue vacuum effects are too weak to impact macroscopic chemistry, but counterarguments point to quantum biology discoveries like photosynthesis's eerie efficiency, where plants seem to harness quantum coherence to optimize energy transfer. If nature exploits quantum weirdness today, why not at life's dawn? What makes this theory revolutionary isn't just its mechanism, but its universality. Unlike Earth-bound scenarios requiring specific geologies or atmospheres, quantum fluctuations permeate all spacetime. Every exoplanet, every nebula, even rogue interstellar gas clouds inherently host this creative potential. The cosmos might not just contain life's ingredients, it could be actively, invisibly coaxing them toward complexity in ways we're only beginning to imagine. Perhaps the ultimate irony, the quantum vacuum we once called empty, might have been life's silent partner all along, its infinite probabilistic dice rolls occasionally landing snake eyes in just the right way to spark chemistry's greatest trick, turning noise into meaning. From lightning-charged primordial soups to quantum fluctuations in the vacuum of space, we've journeyed through 30 astonishing theories about how the universe cooked up life's first organic molecules. Each idea is a brushstroke on a cosmic canvas, some bold and dramatic, others subtle and intricate, but together, they paint a picture of a universe teeming with creative potential. The primordial soup showed us how Earth's chaotic infancy could have brewed life's ingredients in its own waters. Hydrothermal vents revealed how crushing pressures and scorching heat might have forged complexity in the deep. Panspermia turned our gaze outward, suggesting the building blocks of life could have hitched rides on comets, while cosmic dust grains proved even the tiniest specks of matter might be master chemists in the void. What's striking isn't just the diversity of these theories, but how they interlock. Maybe life didn't arise from a single eureka moment, but from a symphony of processes, asteroid deliveries enriching tidal pools, electric fields organizing molecules in the sky, and mineral surfaces acting as molecular scribes. The iron-sulfur world could have powered the first metabolic sparks, while quantum tunneling in deep space nudged fragile molecules toward stability. Even black holes, those notorious destroyers, might have secretly forged organic gems in their violent accretion disks. The beauty of this puzzle is that no single piece tells the whole story. Like a cosmic detective case, each clue leads to new questions. Did radioactive beaches and geothermal gradients work in tandem, creating safe havens for delicate chemistry? Could chiral starlight and magnetic fields have conspired to bias life's handedness from the start? And if quantum fluctuations really did tip the scales, does that mean the universe is inherently rigged for complexity? As we stand at the edge of these mysteries, one thing becomes clear. The origins of life aren't just a chapter in Earth's history, they're a testament to the universe's relentless ingenuity. Every theory we've explored, no matter how wild, reminds us that the cosmos is far stranger and more inventive than we ever imagined. So here's a question to leave you with. If you could combine any two of these theories, like cosmic dust meeting hydrothermal vents, or quantum tunneling supercharging the RNA world, which duo do you think unlocks the most compelling version of life's origin story? Drop your favorite mix in the comments, and let's keep this cosmic conversation going. After all, the next great insight might not come from a lab or a telescope, but from the collective curiosity of minds like yours, daring to piece together the universe's